Welcome to Calculus Lesson 7.1, Cartesian Vectors. Right, so let's start off by drawing a Cartesian coordinate system, just the first quadrant. Okay, so we've got our x-axis, we've got our y-axis, and I've got a point here in my two-dimensional space, and I'm going to call that point P, and it has coordinates a, comma, b. Now, notice that when I label a point, it's given by round brackets. If I was to then go ahead and draw an arrow from the origin going to that point, this would now be a vector. Okay, so now I have the vector u. Now, u is the vector going from the origin to point P. And u, I write like this, a, comma, b. But not with round brackets, but with square brackets. So the point, again, round brackets, excuse me, and the vector, square brackets. Now, the fact that this vector starts at the origin, that means it's a position vector. So again, since it starts at the origin, any vector whose tail is at the origin, you call a position vector. So if I take this arrow vector u with this direction and this magnitude and I move it somewhere else, well, it's still going to be vector u, but it's no longer going to be a position vector. It'll just be an ordinary vector. Now, let me go ahead and draw vector u again here. So there's x, there's y, and here's my vector u. Now notice that u has both x components and it has a y component. So in order to break u down into its components, well, first things first, those components are always perpendicular. For our purposes in calculus, the components will always be x and y. Those of you in physics would have seen that you always broke things down into components that were perpendicular, not necessarily x and y. But anyways, so what I'm going to do is I'm going to take a line from the top of the arrow and I'm going to drop it down to the x-axis. Okay, so I'm going to make a 90-degree angle. Now that line here, that's going to represent the y component of u. So I'm going to call that b. And down here along the positive x-axis, I'm going to have another vector. Okay, this one's pointing to the right, b is pointing up. The arrow pointing to the right along the x-axis, I'm going to call that vector a. Okay, so based on this, we know that vector u is equal to a plus b. Okay, so if you remember how we add vectors, we add them tip to tail. So if I take a and add b to the tip of that, which I have, all right, so the tail of b is attached to the tip of a, the resultant is from the tail of the first vector to the tip of the final vector, which is exactly u. So this is the vector sum expression. Now the fact that these three vectors form a right angle triangle, and they always will, where the components make up the two legs of the right angle triangle, and the actual original vector makes up the hypotenuse of that triangle. Therefore, we can use Pythagorean Theorem to figure out the magnitude of u. So I can say that u squared is equal to a squared plus b squared. Okay, so just something to keep in mind. Now, depending on what u is, how long it is, well, I know that I can break it up into a and b, but both a and b have their own building blocks. Okay, so we're going to now look at building blocks of a and b. Okay, so the building blocks of a and b are essentially going to be unit vectors. Now, whenever you've heard the word unit in math, it always refers to some special quantity being 1. So the unit circle has radius 1. Okay, unit vector is a vector that has magnitude 1. So a unit vector is a vector that has magnitude 1. And we know the magnitude again using this formula, right? So the length of that vector is 1. So I'm going to go ahead and draw a Cartesian coordinate system, only first quadrant again. So here's x, here's y. Okay, so what I'm going to define now are unit vectors in the x and the y direction. So in the x direction, I have a unit vector called I. Let me just draw it like this. It has length 1, and it's in the x direction. So this is I. Now, because it's a unit vector, I don't just have to call it I. I can also give it, instead of putting this arrow on top, I can call it I hat. And that's exactly what it's called, as if it has a hat. Okay, whenever you see the hat symbol on top of a vector, it means it's a unit vector. Now, I can represent the unit vector with the regular symbol as well, but this just makes it more specific. All right, so this vector is 1, 0. Okay, so this implies that it has length 1 in the x direction and length 0 in the y direction, which is exactly the case. All right, so that's a unit vector in the x direction. Now, a unit vector in the y direction will look like this, and it's called j, or j hat. And it has components 0, 1. So it has a length of 0 in the x direction and a length of 1 in the y direction. Okay, so for our intents and purposes, I'm just going to call this I, so 1, 0, and j, 0, 1. Okay, so these are the unit vectors in two-dimensional space. All right. Now, going back to this idea that I have u and I break it down into two perpendicular components, a and b, a is along the x direction, b is along the y direction. Now, if a had magnitude 1, I could just call it I. But a, most likely, it's not going to have magnitude 1. It might have magnitude 5 or 7.3 or 16, whatever the case is. But what I know is that it's going to have magnitude a, and it's going to be in the direction of x, or I hat, or I. Okay, so what I'm going to look at now is this. Vector A has magnitude A, right? So the magnitude of vector A is just A, whatever it is, and it's in the x direction. Okay, now notice that vector I has magnitude 1 and is in the x direction as well. And so what that means is I can take vector A and I can rewrite it as the following. A vector has two components, magnitude and direction. So vector A I can write as the magnitude component, which is A, and the direction component, which is I. Okay, so A is equal to A times I. Okay, so that is still the same thing. These two things are the same. Okay, and I can do the same thing with B. Since B is purely in the y direction, I can say that the vector B is equal to magnitude B, but in the direction of J. I'm used to putting the hat, but our books, they don't use the hat symbol, so I have to get used to that. All right, so that tells me that while U, let's just go up a little bit here, U is equal to A plus B, well, I can rewrite that and say that therefore U is equal to magnitude A along the I direction plus magnitude B along the J direction. So this statement and this statement are the same, okay? All right. So let's actually look at this in a little bit more detail. What if I wanted to take my vectors and split them up? After all, I'm saying that A is equal to magnitude A in the I direction, and I is 1, 0. Okay, so looking at that, if I say that A is equal to A times I, okay, so that means I have A 0 effectively as my vector. Right? If I have the vector 1, 0 as I, and I multiply that by A, I now have A 0. Which means my vector has length A in the x direction and length 0 in the y direction. And I can say that Bj is equal to 0b. And this is the same thing as vector B. Now if I take a0, I can factor out the a, and now I have a times 1, 0. And for vector b, I can just factor out the b and call this 0, 1. Okay, and sure enough, this is I on the left, and this is, and this is j on the right. Okay, so another way to write u is, therefore we can say that u is equal to a0 plus 0b. There are so many ways to represent vectors that are all equivalent to each other. Okay, so looking at this representation, I actually have the vector components visible. Okay, so when I add vectors, I have to make sure that I add the x components together and the y components together. Okay, and I'm going to show you effectively another way of looking at that in the next example. All right. So we're going to look at how we add vectors. Okay, so this is going to be kind of like a derivation, but more of a proof on how we can show that these two things are in fact the same. All right, so let u, so this is vector u, be the vector who has components u1 and u2. And vector v is the vector who has components v1 and v2. Okay, so if I wanted to see what u plus v is, if I'm adding those vectors, so that's going to be u1 comma u2 plus v1 comma v2. Now, using what I just did, I can take a vector and I can split it up into x pieces and y pieces. Okay, so I'm going to take this vector here, u, and I'm going to break it up into two pieces, an x piece and a y piece. So I'm going to split this up into u1 comma 0 plus 0 comma u2. And then take v1, v2 and split it up into v1 comma 0 plus 0 comma v2. Okay, so now that I've split them up, I'm going to go ahead and divide out the constants here. So I'm going to have u1 times 1, 0 plus u2 times 0, 1 plus v1 times 1, 0 plus v2 times 0, 1. Okay, so what I notice is that I have a series of i's and j's here. So 1, 0, that's I. Here's 1, 0 again, that's I. I have 0, 1, that's j, and I have again 0, 1, that's j. Okay, so I'm going to go ahead and replace that. So u1 times I plus u2 times j plus v1 times I plus v2 times j. Okay. Now what I'm going to do is collect my like terms. I'm going to collect the i's with the i's and the j's with the j's. Okay, so that means I'm going to have u1 plus v1 times I plus u2 plus v2 times j. And now I'm going to take I and j and represent them as their original vector representations. That is 1, 0 and 0, 1. Actually, let me just move this down a little bit. Okay, so u1 plus v1 times 1, 0 plus u2 plus v2 times 0, 1. Notice that I'm being very careful with my brackets. When it's a scalar, I keep it as a round bracket, or if it's a point. In this case, it's not a point, it's a scalar. When I have a vector, I have to put square brackets. Make sure you do not put square brackets for a point, or vice versa. You don't put round brackets for a vector. This will be incorrect. Okay, so those of you that studied IB, you would have been used to seeing this kind of a vector being written like this. Okay, or even the same thing with square brackets. We're not doing that anymore. Okay, try to start representing vectors like this. Now, while they're both technically equivalent, I want you to get used to being able to express it in both ways. Don't just get stuck writing things in one way only. Okay, so I'm going to take these constants and I'm going to divide them inside, or sorry, multiply them inside. So this is scalar multiplication, right? So I'm going to take this set of constants, that's just a number, and distribute it to each of the vector components. So now I'm going to have u1 plus v1 times 1, which is just u1 plus v1. If I multiply that sum by 0, I get 0. Plus, again, u2 plus v2 times 0, that's 0. And then multiplying that by 1, I have u2 plus v2. Okay, so last step, add the x pieces together, add the y pieces together. And we're going to have u1 plus v1 plus 0, which is just that, and then comma 0 plus u2 plus v2. Okay, now if you're looking at this and saying, well, I could have figured that out right from the beginning, add the x components, add the y components, well, at least now you see how it's done using the i's and the j's and how that just properly flows together into the original sum. Okay, so now we have our sum of the vectors. All right, so we are now officially 1/4 of the way through the lesson. So this 7.1, it is an 80-minute lesson. Okay, since it's a 40-minute class, that's why 2 days have been distributed for this. Okay, so if you need the 2 days to cover the video and the homework, you have 2 days to do it. All right, so we've got that. Now we're going to do a very similar idea, except this time we're going to multiply a vector by a scalar k. Okay. Multiplying a vector by a scalar k. Scalar is just a number. Okay, so you're taking a vector and you're multiplying it by a number. So let u, again, be the vector u1 comma u2. And k is just our constants, so we're going to say it's an element of the real numbers. Okay. If that's the case, then k times u is going to be k times u1 comma u2, right? Now if I take u1 comma u2 and I break it up into its two separate pieces like before, I'm going to have k, and then here I'm going to just put a bracket here. So I'm going to have u1 comma 0 plus 0 comma u2. So just breaking it up into its x and y pieces. Okay, after which I'm going to factor out u1 and u2. So that's equal to k u1, should be square bracket, 1 comma 0 plus u2 square bracket 0 comma 1. There we go. Now you see how I have a scalar out here? I'm going to take that number and I'm going to multiply it inside again. So I'll have k times u1 times this vector plus k times u2 times the next vector. So k u1 times 1, 0 plus k u2 times 0, 1. And finally, I'm going to take that scalar number, that value, and I'm going to multiply it to each piece inside of the vector. Okay, so that means I'm getting ku1 comma 0 plus 0 comma ku2. And finally, adding the x and y pieces together, this is going to be ku1 comma ku2. Okay, so really all this is showing is that, well, any scalar multiple of a vector u is just k times u. Okay, so these two things are scalar multiples. That means they are collinear. So let me just write this down. They are scalar multiples. Therefore, they are collinear. Therefore, they are parallel. So if this new vector is called, let's say, w, then w is parallel. It's collinear, and it's a scalar multiple of u. And all three of those things mean the same thing. Okay, so we've gone through some theory. Let's do a formal example. Okay. So example 1. And by the way, I'm hoping that as we go through this, you have been taking your own notes. So as I'm doing this, just pretend this is as if I'm writing it on the board. You should be writing this down in your notes. If you need more time, if you have to review a concept, it's actually really convenient because you can pause the video and replay a certain section. Okay. All right, so example 1. Given vector A, so that's 5, comma, -7, and vector B, which is 2, comma, 3, determine, right, so there's actually going to be a lot of parts to this question. Part A, we have to determine an expression for A in terms of its horizontal and vertical vector components All right, horizontal and vertical vector components. So those are the x and y pieces, essentially. So all that means is I take my vector A, which is 5, comma, -7, and I break it up into 2 other vectors. One vector representing the horizontal, one vector representing the vertical. So some vector plus some vector. Okay, so we did this in the previous 2 examples. I can break this up into an x piece and a y piece. So the x piece is going to be 5, comma, 0. And the y piece is going to be 0, comma, -7. So that's it for part A. For part B, determine an expression for vector B in terms of I and j. And by the way, if you want to try this problem, just pause the video, try it, and then you can play it and see if you're doing it properly. Okay, so vector B is up here. I know that I reflects the x component of 2 and j reflects the y component of 3. So if B is equal to 2, comma, 3, I can rewrite that as 2 times vector I plus 3 times vector j. Okay, moving on. Part C. Okay, so now we want to determine what 3a is equivalent to. Okay, so this is just a scalar multiple. So if I have 3a, that means I'm just multiplying the vector a, which is right here, by 3. So 3 times 5, comma, -7. So that's 15, comma, -21. Okay, so that's it. D, A plus B. Okay, so you can actually look at that in 2 ways. You can call that a sum of vectors. It's also a linear combination, okay, because you're combining a sum of 2 vectors, each of which has some product scalar multiple of. Okay, so even though it's 1 times A plus 1 times B, that's still a product, right? It's still a scalar multiple. So we have a scalar multiple of each added together. That's a linear combination. Okay, so A plus B, well, the vectors are right here. So 5, comma, -7 plus 2, comma, 3. I know that I'm adding x to x and I'm adding y to y, right? These are like your like terms. When you add vectors, you always end up with 1 vector in the end. So 5 plus 2 is 7. -7 plus 3 is -4. Okay, so that's A plus B. Okay, part E, 2a minus 4b. Okay, so 2a minus 4b, so this is going to be 2 times 5, comma, -7 minus 4 times 2, comma, 3. All right, so what I'm going to do first is take these constants and multiply them and distribute them inside. So that way I have one vector here minus another vector here. So 2 times 5, oh, by the way, let me draw those arrows in so you see what I mean. 2 times 5 is 10. 2 times -7 is -14. 4 times 2 is 8. And 4 times 3 is 12. Okay. So this results in 1 vector. Okay, so now I do 10 minus 8. That goes in the x component. 10 minus 8 is 2. And then -14 minus 12, that's -26. Okay, so that's the final answer for part E. Now, part F is going to be, well, it's going to be a little interesting. Let's put it like that. Okay, so we're going to go on to a new page here. So hopefully that's been okay so far. Okay, so part F, we have to find two unit vectors collinear with A. All right, so let's find this. Couple of things, you got to break down the question here. A unit vector, I know they're going to have magnitude 1. I can determine that and I can work that out in the last step of the problem. Right now I got to figure out two vectors that are collinear with A. So remember, collinear means they're parallel, okay? So they're scalar multiples of each other. Okay, so the first thing I want to identify is that a vector collinear with A is k times A, where k is an element of the real numbers, right? K can be an integer, it can be a constant. Sorry, camera lost focus there for a sec. Okay, it can be an integer, it can be a constant, it can be a decimal, whatever it is. Okay, so I need some constant times A. Now, we want the k value such that we get a unit vector, right? So such that the magnitude of k times A is equal to 1, right? Otherwise, we wouldn't have a unit vector, right? So we know that we need k times A. Okay, so that means I need k times A, which is 5, -7. Okay, that is, so take your constant in front and distribute it to each of the interior pieces. That's 5k, -7k. So whatever k value you want to plug in, that's going to be a vector that is collinear with A. Okay. Now, again, we need to know that the magnitude is equal to 1. From the very first page where we were studying this section, 7.1, we said that the magnitude, so let me actually just bring it up here for a second. From the first page, we said that the magnitude of a vector u was equal to, well, the sum of the squares of the other two sides, but then you need to square root that as well, right? So u would be equal to the square root of a squared plus b squared, right? So the sum of the squares of the x and y's. So that's what we're going to be doing here too. We're going to be using Pythagorean Theorem. So the hypotenuse squared, so ka squared, is going to be equal to the magnitude of the x piece squared, which is 5k, plus the magnitude of the y piece squared, -7k. The reason why we do absolute value, the magnitude, is so that the minus signs, they don't mess you up. But in reality, well, you know, if you square it, it's going to become positive. So, all right. So what do we get? I know the left side here. I know that the magnitude of ka has to be 1 in order for me to have a unit vector, right? So that means I have 1 squared, which is 1 on the left. Okay, so 5k squared, that's 25k squared. And then on the right side here, I'm going to have plus 49k squared. Okay, so 49 plus 25, that is 74. So 1 is equal to 74k squared. So k squared is equal to 1 divided by 74. So then k, if I square root both sides, I'm going to have root 1 over 74. Now what you got to be careful here is that I don't just have the positive root, I have the negative root as well, right? So if I square both sides here, if I have negative root 1 over 74 and I square it, I'm going to still have positive 1 over 74. So make sure you don't miss out on that second solution. Okay, so therefore, okay, so let me just circle this. And therefore, the two unit vectors are, so remember it's k times A, right? So k times this vector, right? So essentially what it's going to be is plus 1 over, root 1 over 74 times 5, -7 and minus root 1 over 74 times 5 comma negative 7. Now since these are vectors, I actually have to make these square brackets. So let's make sure I do that. And of course we can then write each of these vectors a little bit better. We can write this as 5 over root 74, comma negative 7 over root 74. And this bottom one is going to be negative 5 over root 74, comma positive 7 over root 74. So I guess either way that you want to write it, whether it's like this, or whichever one you prefer, it's fine, as long as you have both answers there. Okay, so that officially marks the halfway point of 7.1. Okay, all right, so let's keep going. Part G. Now we're going to figure out the absolute value of A minus B. All right, so before I do that, I'm going to actually figure out A minus B first, and then I'll figure out what the magnitude is. So remember, absolute value in vector language means magnitude. How long is it? And I know that when you add or subtract vectors, you just get another vector. So I got to figure out what the length of that new vector is. So A minus B. Here we go. So we're going to have 5 comma negative 7 minus 2 comma 3. So x minus x. So 5 minus 2, that's 3. And negative 7 minus 3, that's negative 10. So there's my vector. Okay, so now in order to find the magnitude, well, you know how to do this. Just visualize it, right? So this vector has an x component of positive 3, y component of negative 10. That's going to be in quadrant 4. Okay, so 5x, and you have y up here. So 3, negative 10, that's somewhere like this, right? So to find the magnitude, you have to break this up into two vectors, an x piece and a y piece, right? And you take, well, effectively you take Pythagorean Theorem, and you figure out the length of the hypotenuse. So the length of the hypotenuse here is A minus B, magnitude. Okay. So A minus B magnitude is going to be equal to the square root of 3 squared plus negative 10 squared. So the square root of 9 plus 100, or the square root of 109. It's a magnitude, so you have no direction, just a value. Okay, so let's keep going. Now we're going to look at a Cartesian vector between 2 points. Okay. Let's say I've got 2 points. So let P1 be the point x1 comma y1, and P2 will be the point x2 comma y2. Okay. Let's grab our rulers, and we're going to draw the first quadrant of our Cartesian coordinate system. So there's my y-axis, there's x, and let's say my points are here. Okay, wherever they are, I have my 2 points. So P1 and P2. Okay. So what I'm going to try to do here is come up with an expression for P1, P2. So for the vector going from P1 to P2. Eventually, what I'm trying to do here is figure out a way to use vectors to determine the distance between these 2 points. Now, because you've studied math before, you already know how to calculate the distance, but we are reinforcing that by showing you how to do it with vectors. Okay? Now, a couple things. You know that in order to get a vector, so let's say if I want P1, P2, let me actually just sketch that here on the diagram. So P1, P2 is the vector starting from P1 and going to P2. So the tail's at P1 and the tip's at P2. So it looks like that. Let's say I want to add 2 vectors to get to that vector. If I want to add 2 vectors to get to this, the arrows have to be arranged tip to tail such that the tail of the first vector starts here at P1 and the tip of the final vector is here at P2. Okay, so the way to do that would be to draw a vector from P1 to the origin. So I'm going to draw an arrow like this, and then have another arrow go from the origin to P2. Okay, so this vector here is P10, and this vector here is OP2. Right, so when you add these vectors tip to tail, as they are right now, the resultant, which goes from the tail of the first vector to the tip of the final vector, is P1, P2. Okay, so therefore I come up with the expression that P1, P2 is equal to P10 plus OP2. Okay, so I'm going to take this and I'm just going to flip it around. All right, because I know that addition is commutative. So this is the same thing as OP2 plus P10. All right. Now, from what you remember, opposite vectors, if I have AB, well, that's equivalent to negative BA, right? BA is the opposite of AB, but if I stick a negative in front, that puts it in the right direction again. So now these two are the same. So what I'm going to do is take P10 and I'm going to replace it with negative OP1. So therefore I have OP2 minus OP1, or you can call it plus negative OP1. Notice that now I've got the vector OP1. The vector OP1 is the arrow that starts at the origin and goes to point P1. And if you remember, let me get our first slide up again. Here, the very first thing we looked at was the vector u going to point P. And we said the vector u was a position vector because it started at the origin. So something I'm going to show you now, another way of writing vector u is OP. Okay, so when the vector is written like this, you automatically know it's a position vector. By saying OP, I'm saying this is the vector that starts from the origin, always origin, and it's going to the point P. Automatically you know it's a position vector, right? And the point, whatever it is the second letter in the sequence. All right, so going back to what we have here, I have OP2 minus OP1, OP1 being the vector from O to P1. Okay, so that means I can represent it with whatever this point is, but in a vector form. So if the point is x1, y1, then the vector would be x1 comma y1, but with square brackets. Okay, so I'm going to replace these two with their vector. So OP2, that's going to be, well, that's this vector. That's x2 comma y2. And OP1 is x1 comma y1. Now you know how to subtract vectors. You subtract the x components and you subtract the y components. So I have x2 minus x1 comma y2 minus y1. Now keep in mind that's the vector p1, p2. What I said at the beginning was we're trying to figure out a way to figure out the distance between these points. But guess what? The distance between points P1 and P2, that's equivalent to the magnitude of the vector between P1 and P2, because the magnitude of this vector is telling us its length. And if we know its length, we know the distance. So now we are going to try to find the magnitude of P1, P2. Now you know how to find magnitude. We've been doing this in many of the problems so far. What I need to do is use Pythagorean Theorem. I've got an x component, I've got a y component. The hypotenuse is going to be the square root of the sum of the squares of the x and the y pieces. Okay, so the x pieces, x2 minus x1, and the y pieces, y2 minus y1. And, well, sure enough, there you have it. There is your distance formula between 2 points. All right. So there's that proof. Okay, so now we're going to move on to another example. All right. Find the coordinates and magnitude of each vector All right, so for part A, we want to find the magnitude of AB for A. So the point A is at 1, 3, and point B is at 7, 2. All right, so we're going to use that formula. We already know it. If you ever forget it, because this formula, well, actually, it might be in the data booklet, but it's something that you can easily derive again. Okay, so the distance between AB, so the magnitude of AB is going to be, well, the square root of, there are x components subtracted and their y components subtracted, each of those squared. Okay, so I'm going to have x2 minus x1 squared plus y2 minus y1 squared. Okay, so A, which is 1, 3, there's my x1 and there's my y1. And for B, which is 7, 2, there's again my x2 and y2. All right. And you can do this piece by piece, or you can do it all together as I have here, up to you. Okay, so x2 minus x1, that's 7 minus 1 for the x, and y's, it's going to be 2 minus 3. All right, so we end up getting square root of 6 squared plus negative 1 squared. So 36 plus 1 is 37. So we get square root of 37. That is the magnitude of each vector. The coordinates of the vector, okay, so the coordinates we can actually do like this. So AB is just x2 minus x1, comma, y2 minus y1. Okay, so since we already figured out what those values were, they're 6 and negative 1. So we just have 6 comma negative 1. This is the vector. Okay. And there's the magnitude. Okay. If you have points with negative signs, just be mindful to be careful dealing with the negative signs, subtracting negative signs, and religiously using your brackets. Okay. So we are now 3/4 of the way, well, almost 3/4 of the way through the lesson. Okay, next. So this is example 3. All right. Write a geometric vector in Cartesian form. Actually, this isn't exactly the example quite yet. Write a geometric vector in Cartesian form. Okay, so this is just helping us to understand the difference between, well, what a geometric vector is and what a Cartesian vector is. So you understand what the difference is. All right, so let's draw our Cartesian coordinate system, one quadrant. So there's x and there's y, and I've got, let's call it vector v. Okay, so this is vector v, and vector v is at an angle theta to the horizontal. Okay, so that is a geometric vector. It's an arrow representation, it's a visual representation of the vector. The length indicates its magnitude, and the direction is indicated by angle theta. So remember, you can give the direction from what we saw in lesson 6.1 through a true or azimuth bearing or through a quadrant bearing. Now, if we want to change this to Cartesian form, the first thing we need to do is drop a vertical dashed line from the tip of the vector to the horizontal axis. So we're going to drop a line like that. And so now that is going to represent the vertical or the y component of vector v. So that is essentially vy. And I can also draw this arrow on the x-axis. Okay, so this is the horizontal component. We can call that vx. And so vx is traveling to the right, vy is traveling up, and v is going up and to the right. Okay? And of course, vx and vy are perpendicular to each other. Okay, so in order to write the vector in Cartesian form, what that means is I just have to write it, well, in the square brackets with a comma in between, and I need to write the components in terms of the sine and cosine of the angle. So Cartesian form means, I'll just write this here, write the components in terms of the sine and cosine of the angle. Okay, so this will be something that you'll get used to. Okay, so if I look at theta, sine of theta, and I'm only going to do this once, afterwards I'm going to use the shortcut, sine of theta is opposite over hypotenuse. So it's Vy over V, essentially, right? So if I wanted to rearrange for Vy, I multiply the V up to the left. Oops. So that's going to be V times sine theta. Okay, so likewise, if I look at cosine of theta, it's adjacent over hypotenuse, so that's Vx over V. So therefore, if I rearrange this for Vx, it's going to be V cosine theta. So what I notice is that as long as I drop the line from the vector to the x-axis, the x component will always be equal to the hypotenuse times cosine of the angle between the vector and the x-axis. And the y component will always be the magnitude of the vector times sine of the angle. Okay. Again, the angle has to be between the vector and the x-axis. If it's not, then these two actually get reversed. All right, so that means here, vector v, it's going to be the magnitude of v. Oops. So for the x component, it's going to be magnitude of v times cosine of theta. And for the y, it's going to be magnitude of v times sine of theta. And that is writing the geometric vector in Cartesian form. Okay, so now that we understand that, let's actually do an example using that knowledge. Okay. So now this is example 3. All right. Write 200 newtons at 20 degrees to the horizontal in Cartesian form. Okay, so this is the geometric form, right? We have the magnitude, we have the direction. We have to write this in Cartesian form. Draw a picture. Okay, so a quick sketch. There's x, there's y, 20 degrees to the horizontal. It's going to look something like this. So there's 20 degrees, and the length of this thing is 200, and the units are newtons. Now, if you're interested, Newton is the unit of measure for force. Otherwise, well, you don't need to worry too much about that. But since it's force, we can actually label it with capital F. So we can call this vector force with the arrow on top. All right, so F is going to be equal to the magnitude of F times cosine of theta for the x component, and the magnitude of F times sine of theta for the y component. And I can use this formula because the angle is given between the vector and the x-axis. If it's not, you just have to figure out what that angle is going to be. All right, so the magnitude of the vector is 200. So that's 200 times cosine of 20 degrees, comma 200 times sine of 20 degrees. All right, so all we need to do is grab our calculators and figure out what this is going to be equal to. So 200, make sure your calculator's in degrees, by the way, times cosine of 20. So that's about 187.9. If you want 3 sig figs, that would be 188. And then 200 times sine of 20, that's 68.4. Okay, so that's the same vector, but written now in Cartesian form. So that is the final answer. Okay. We have one more problem to do, and this last problem, it's a bit long, but it's similar to a problem we did before. However, the way in which we're going to solve it is different. Okay, so we're going to be adding vectors, but instead of adding them using sine law and cosine law, we're going to be using vector components. Okay, so this is Example 4. All right. A ship's course is set to travel 23 kilometers per hour relative to the water on a heading of 040 degrees. Okay, I want you to notice that is a true or azimuth bearing. There's 3 digits, so that means I'm measuring this clockwise starting from north. A current of 8 kilometers per hour is flowing from a bearing of 160 degrees. Important, it's telling you it's flowing from this bearing, not to this bearing. Okay, I'll show you how that's different when I start sketching the picture. Okay, part A. Write each vector as a Cartesian vector. Okay, so remember, with Cartesian vectors, the angles are always measured relative to the x-axis. In this case, it's going to be, well, from the relative to the east. East would be the positive x direction. Okay. So for part A, we're going to go ahead and sketch this out. So I've got, well, I'm going to draw the top right quadrant a bit bigger here, but sure enough, that's north, east, south, and west. I know that I'm dealing with the compass directions because I'm dealing with bearings. All right, so I know that the ship is set to travel 23 kilometers an hour. That's its speed, and it's heading at 40 degrees. So again, because that's a true bearing or azimuth bearing, let me just... So this is a true / azimuth bearing. That means you start at north and you go clockwise. All right. So that means clockwise from north 40 degrees. It's going to look something like this. Okay, so we've got 23 kilometers per hour, and this is 040 degrees. Okay. Since this is the ship moving, I'm going to call this vector S. You can call it whatever you like. It's a vector, so I have to put the symbol on top. And I know that the Cartesian vector is going to have an x component and a y component separated by a comma. Okay, so the x component is the magnitude, which is 23, and it's going to be 23 times cosine of the angle. This is where you got to be a bit careful. What I said earlier is that you can plug the angle right away as long as it's the angle between the vector and the horizontal axis. Here, 40 degrees is between the vector and the y-axis. So some of you might just want to say, well, the x component is going to be 23 times sine of 40. Otherwise, if you want to use the given formula, you got to figure out what the angle is between the vector and the x-axis. So that's just going to be 90 minus 40, which is 50 degrees. Okay. So that means I have 23 cosine of 50 degrees for my x and 23 sine 50 for my y. Okay, so just take a step back and make sure that's okay. If you had done it the other way around, you would have used sine of 40 degrees here and you would have used cosine of 40 degrees here. They are the same thing, and you can check that on your calculator. Okay, so if you actually check cosine of 50, it's about 0.64. If I do sine of 40, it's 0.64. Oh, unfortunately, the light was in the way. Sorry. Sine of 40 is 0.64, and cosine of 50 is 0.64. They're the same. All right, so that is S. Now, I can absolutely calculate that a little bit more exact, but I'm going to leave that actually until a later part, so until part B. All right, So that is the ship's vector. I know now a current of 8 kilometers per hour is flowing from a bearing of 160 degrees. So I'm going to go ahead and draw my, axes here. This time I'm going to draw all 4 quadrants equally. So north, east, south, west. You do not need to label all 4 compass directions. You have to label at least north. Usually north is the minimum. Okay, so now because this is coming from a bearing of 160 degrees, let's figure out where 160 degrees is. Well, we're going to start at north, and we're going to go clockwise 160. So 180 is the south line. Okay, the 90 is here, so 160 is going to be somewhere between south and east, closer to south. Okay, so I'm going to draw this. So I've got 160 degrees. Now if that's 160 and I know that a straight line is 180, that makes this angle in here 20 degrees. Now what you got to be careful of is that the question says the current is from this direction. It's not going to that direction. It's coming from that direction. So if I keep the arrow like this, it's implying that the current's going in that direction, right? The direction the arrow is headed. But it's coming from this direction. That means it's going in the opposite direction. And actually, quite literally, the opposite direction. So I'm going to continue this arrow along a straight line above the horizontal axis. Actually, let's just do it like that. Okay, so if it's coming from this direction, it means it's going to the direction of north, 20 degrees west. Okay. Now, the magnitude is still 8 kilometers per hour. Okay, the fact that it's going in a different direction doesn't change that. It's still a magnitude of 8, except now the direction is 20 degrees west from north. So when I want to give my Cartesian vector representation of this, okay, so let's do this. Let's call this vector C. Okay, it's current. Okay, so the current, again, it's given by a vector. There's a comma. Okay, so the magnitude is 8. And we're going to have cosine of some angle for x and sine of some angle for y. Okay, so what's that angle? This one, you got to be doubly careful. Okay, so if you go ahead and say, well, okay, I know I'm not going to fall into the trap of plugging in 20 degrees because that's the angle with respect to the y-axis, not the x. You would be right. I have to figure out the angle with respect to the x-axis first. But the problem is, so if you figure out, okay, well, this is 70 degrees, well, that's fine, but then you have to realize that with this vector, the x component's actually going left and the y component's going up. Okay, so in all our examples so far, the vector has been in the first quadrant, which means that when I draw my vector, so let's say this is my vector u, when you break it up into its x and y pieces, the x component is going to the right and the y component's going up. So you have ui and ux. Okay, this time my vector is going up and to the left. Okay, so in order to construct that vector, well, I need one vector going left, so let's call this v. This would be vx, and then my y component is going up, vy. Okay, so either if you plug in 70 degrees here, you got to remember to put a minus sign here. Or the other way is always remember the angle has to be measured relative to the positive x-axis. So the angle measured from the positive x-axis, well, that's 90, right, between north and east. Add 20 to that, and you have 110 degrees. So that's the angle that I plug in here. Now, what I was just saying is if you want to use 70 degrees, that's fine. Just keep in mind that the x component's got to be negative. The y component will still be positive. That's fine. So this is the same thing as, if you want to write it like this instead, 8 cosine 70 degrees, but stick the minus in front, and then you can still have 8 sine 70 degrees. Okay, and sure enough, we can grab our calculator and make sure that that's indeed correct. Okay, so 8 times cosine of 110 is minus 2.74 approximately. And then minus 8 times cosine of 70, again, minus 2.74. So it's about the same. So we've got that. So we've got our vectors. So this would be half of my final answer for A, and the other half would be this vector up here. Okay, so hopefully that's all right. There we go. So we wrote both vectors as a Cartesian vector. The last part of this question, and this will be the end, finally, I'm sure you're waiting for that to come. Part B, determine the resultant velocity of the ship. Okay, so we're going to have to do that on another piece of paper here. So B, determine the resultant velocity of the ship. Okay, so the resultant velocity of the ship, if we want to call that VR, well, I mean, we've got the ship trying to head in a certain direction, but then the current is also affecting it. We have to add both of those contributions to see what the net result is. Okay, so each of these was its own vector. So I'm just going to lay this out from the beginning. S we found up here. So let me just bring that back. S was 23 cosine 50 degrees, comma 23 sine 50 degrees. Okay, and C was 8 cosine 110, or you can use minus 8 cos 70, and then 8 sine 110. Okay, so I'm just going to remove that now. Okay, so if I actually punch these in my calculator, so I've got 23 times cosine 50, that's about 14.78. 23 times sine 50, so that's 17.6. 8 cosine 110, that's minus 2.736. And 8 sine 110, that's 7.5175. Okay, so let's go ahead and write this in. So 14.78, comma 17.6 plus negative 2.736, comma 7.5175. Now I realize the number of decimal places I've kept is not exactly consistent, but that's okay. All right, so I need to combine the x terms and the y terms. So that means I'm going to have in the x 14.78 minus 2.736. And in the y, I'm going to have 17.6 plus 7.5175. Okay, so we end up with 12.044, comma 25.1175. So that's, well, that's the vector. We have to determine the velocity and the magnitude. So we're not giving our answer as a Cartesian vector. We're giving our answer as a geometric vector. We have to say that therefore the resultant velocity of the ship is this many kilometers per hour, and it's at this angle relative to north or relative to south, whatever it's going to be. Okay, so in order to find the magnitude of the velocity, well, this is telling me the x and y components. So the x is about 12 and the y is about 25, and the resultant, well, that's going to be the magnitude of the velocity. So I'm going to use Pythagorean Theorem. So the magnitude of VR is going to be equal to the square root of the sum of the squares of the x and y components. 12.044 squared plus 25.1175 squared. So 12.044 squared plus 25.1175 squared. And then square rooting that, we're going to get about 27.9. And remember, the units are in kilometers per hour. So there's the magnitude. Now for the direction. Okay, so if I have 12.044 in the x and I have 25.1175 in the y, we always state the direction of the resultant relative to the initial vector. So it's always the angle between the first and the final vector. So, or rather the first and the resultant. So what you're going to notice is you're always going to use tangent of theta to avoid using the new calculated value. So tan theta is opposite over adjacent So 25.1175 divided by 12.044. Okay, so grabbing our calculator, 25.1175 divided by 12.044. Taking the inverse tangent of that, and we get 64.4 degrees approximately. Okay, now based on the picture, I mean, you see this direction here, this is effectively east, and that's effectively north. So that means it's east 64.4 degrees toward the north. But if you remember from 6.1, I said that in quadrant bearings, you always start from north or south, and then you go east or west. Okay, so I don't want to give the answer relative to this angle. I'm going to give it relative to another angle. So I'm going to call this angle here relative to the north side alpha. Okay, and alpha is going to be 90 degrees minus theta. So 90 degrees minus 64.4 degrees, which is, so 90 minus answer, 25.6 degrees. Okay, oh, let's get that back in view here, 25.6 degrees. Okay, so that means that's from north, 25.6 degrees toward the east. So therefore, my final answer, the resultant velocity is approximately, let's just call this 28 kilometers per hour. And the direction is, well, a couple things. You can either say north, 25.6 degrees east, or you can say that it's 28 kilometers per hour, and the direction is at a bearing of 0 to 5.6 degrees. Okay, so if you're looking at that and you're a little bit confused, okay, well, I thought that for a bearing, true bearing, you need 3 digits. Yeah, that's for the whole number part. If you put a decimal, that's extra. Okay, but the whole number part, I have 1, 2, 3 places. If it's easier, you can just quote the direction like this. Okay, so we have finally arrived at the end of lesson 7.1, okay, Cartesian vectors. So make sure to review this lesson, make sure it's okay. If you need further reinforcement, you can consult the recommended pages and examples in the book, although they are very similar to these examples, after which give the homework problems a try. Okay, so stay tuned next time for video 7.2.